Okay.
Okay, so welcome everybody to today's edition of the Quasiworld seminar. So our first speaker today is Sam Peters, and he will tell us about entropy of transcendental functions. So please.
Yes, thank you, Mario, and thanks for the invitation. Well, also to Misha, and I don't know who the other organizers are. There will be nothing quasi in my talk. It will be about entropy of transcendental functions, so complex dynamics. And I may mention some results in higher dimensions, but it will all be, the focus will be on one-dimensional complex dynamics. And I'll talk about an ongoing project with Leandro Arosio from Rome, Miriam Benini, who is in Parma, and Erik Fornaess, who is here, I just saw, but also in Norway. So the question is, what is the entropy of an, I cannot see the top of my screen because of the zoom. Well, I know it says transcendental functions.
Yeah, we can see it.
You can see it, great. So here I made a picture of a well-known example. I'm sure Nuria has seen it a million times. The sine of z over 2, which is an attracting fixed point at the origin here in the middle. And of course, the sine is always on the real axis is always between -1 and 1. So the real axis is mapped to a small interval from -1/2 to +1/2, which is this small blue disk, the intersection with the real axis. And that's contracted to the origin. So on the real axis, nothing interesting is happening, but in the complex plane, a lot of interesting things are happening. I try to draw the attracting basin in the colors. So blue and red, those show different stages of how long it takes to get to this little blue circle in the middle. And then you see lots of white here and on the top and in the bottom. But really, it should all be colored. So white is, the computer can't handle it anymore because the basin of attraction actually is dense. And the remainder is a collection of curves that, all have, on the curves you go to infinity, and the endpoints, well, you have interesting behavior on the endpoints. And we'd like to describe what the entropy is of such a function. I won't give the definition of entropy in detail, but let me show you a video. Nuria has already seen it, but I hope you don't mind seeing it a second time. I had some actors acting out the definition of entropy. So here is two kinds of custard, chocolate and vanilla. So my daughter is going to pour some chocolate custard, and then my son vanilla, and you see two colors. And then if you take an irrational rotation, it's not mixing, but if you mix with a spoon, it is mixing, and the custard slowly turns light brown, and there it's gone. Light brown, so it's a mixing dynamical system, and the entropy is the rate at which it turns light brown. So if you speed up the video twice as fast, then the entropy is exactly twice as large. So what's the entropy of a transcendental function? Well, let's go back to some very classical results about rational functions. So here's a result from the 70s. It's really two results. The fact that the topological entropy on the left is at least the log of the degree. That's due to Misiewicz and Pesitsky. I think that was better. And then Gromov, late 70s, proved the other direction. The first result holds in much greater generality. It has nothing to do with holomorphic maps. And Gromov's result really uses holomorphic maps in a very essential way, but holds in all dimensions. And then Lubitsch also proved the result of Gromov independently. So, and this holds for any anamorphism of projective space, complex projective space. And it has also been generalized to other maps in higher dimensions. For example, by Smiley, early 90s, who proved it for complex Hénon maps. And then what I'm really after in this talk is the metric entropy, or the measure theoretic entropy is a better name. And that's in one dimension due to Brolin for polynomials, and then Ljubich, and independently Ferreira, Lopez, and Magnier, who proved that there is a unique measure of maximal entropy. So only one measure, one ergodic measure with that same entropy. For all other measures, for all other ergodic measures, you have strictly lower entropy. So that's the situation in one dimension. So in for rational functions. For transcendental functions, we know that the topological entropy is infinite. So confirming what my bachelor students always say, that a transcendental function, that's a polynomial of infinite degree. So if the degree is infinite, then log d is infinite. So a transcendental function should have infinite degree, and indeed. But this so we proved this with Miriam, Benini, and Erik Fornaess a few years ago. And then suddenly Walter Bergweiler from Kiel remembered that there was a PhD student in Kiel who left mathematics, but he proved this result also in his PhD thesis, never published it, and that was Marcus Wendt. So we contacted Wendt, and he's put his paper also on the archive now, so you can find it there. And what was really great about this paper is that our results used estimates on the hyperbolic metric in the complex plane, and we didn't see how to make it work in 2 dimensions. But Marcus Wendt, he had a very different proof using. Well, there you have a quasi-normality, different kind of quasi, and Alfor's 5-Alins theorem, and that proof we could generalize. So the result also holds for transcendental Hénon maps. So some family of transcendental maps in 2 variables, thanks to the proof of Marcus Wendt. So the natural question now, I think, is does there always exist an ergodic measure of infinite entropy? Which is what you would expect, and is this measure unique? And if so, can you make this? Is the support equal to the Julia set? Or if it's not unique, can you make sure the support is equal to the Julia set? And there are many more questions that you could ask. And maybe just as interesting is, how do you construct this measure? What properties does it have? And I'll get back to that soon. So what is known? Well, there's a result of Christensen and Fisher, who proved that for any transcendental function, there does exist an ergodic measure of positive entropy, and it's supported on the Julia set. But their proof is really not constructive. This showed just if you don't have that, then you have a normal family. So they cook up some symbolic system. So basically, they get a Cantor set, and on that Cantor set, that's a Cantor set for a very large number of iterates. So they don't get any lower bound on the entropy. The entropy is positive. It's a shift map on a Cantor set, a very slow shift map, but there's no estimate from below. And the support is not the whole Julia set, it's just a subset of the Julia set. And then there is a lot of work by a lot of authors also on thermodynamic formalism. And that also provides, at least for some classes of transcendental functions, conformal measures. Now, these are not invariant, but then there's something called Gibbs states, and those are invariant measures. And I don't know yet the extent to which that is related to what we are doing. I'm trying to figure that out. And I also am not sure what they can say about the entropy of those measures. But I just want to mention those results. Now, let's go back to the proof for rational functions due to Ljubich. So Brolin first proved it, at least something like 20 years earlier, I think, for polynomials using potentials. But Ljubich proved it by pulling back point masses. So you put a point mass at a point W. If you're familiar with the field, you should not take the wrong point. So there are at most 2 wrong points, exceptional points. You should not take that one. z squared, you should not take 0 and not take infinity. You take any order point and you look at the preimages under an iterate f to the n. So look at all preimages and you give them the same mass such that it sums up to 1 again. You have to count with multiplicity. Then you get a new probability measure. And as n goes to infinity, these measures converge to the unique measure of maximal entropy log d. And its support is the whole Julia set. So to my mind, that this theorem is how I think about complex dynamics, how I think about what the Julia set looks as the accumulation set of preimages, or many other ways you can do it using the accumulation set of periodic points. It all converges to that same measure. So it would be great if we could have such an insightful way of thinking about arbitrary transcendental functions, but that's a lot to hope for, and I'm certainly not going to present a result like that. So the question is, could such an approach work for transcendental functions? Well, a problem is that almost every point W has infinitely many preimages. So you cannot give the same weight to all the preimages and still deal with probability measures. So we want to look at situations where we give different preimages different weights. But you can imagine that you need inspiration in order to do that, because for every single point, you have to distribute the weight 1 over all its infinitely many preimages. And well, how do you come up with a way to do that? So we want to find weights. So for each W, we want to find a probability vector Vi and define the pullback of that Dirac mass by taking a sum over Dirac masses with weights, and repeat, and hopefully you do it in such a way that that converges to a measure that's not obvious, and then you want that measure to have infinite entropy. So we need some inspiration. So let's discuss how it's possible ways to do it for rational functions that are a little simpler. So here I took a very specific kind of quadratic polynomial for which the Julia set is a Cantor set. And well, here's the potential, the Green's function I sketched. But this is not going to be the way to do it for transcendental functions, because the Green's function here uses that you have a super attracting fixed point at infinity that's very different from transcendental functions. So here's what's done for in the proof of the theorem by Lubitsch. You take the red point, it's W, and you look at its preimages. That's the 4 blue points. Well, I took 2 iterates to get the 4 points. Then I took 4 iterates to get the 16 green points. And I think the gray points are something like 15 iterates, and you see already very precisely what the Julia set looks like. But as I discussed, this is difficult to do for transcendental functions. So here it's a Cantor set, so you have a symbolic dynamical system. Let's think about that. You have just a shift map on your space of sequences in 0 and 1, and you have, since you have a Cantor set, you have a nice homeomorphism between the space of sequences and your Julia set. So if you define a Markov chain on this set of just 2 states, so you need to find a P and a Q probabilities, then if you have a Markov chain that induces an invariant measure on your space of sequences, and it turns out that the maximal entropy rate, log 2, which is really the same as the entropy of the invariant of the shift map on the space of sequences, is obtained only for when you take P and Q both equal to half. And for any different choice, you get a different measure. So in fact, you get infinitely many different measures, but there's only one for which you get log 2. So the stationary measure is a half, and the invariant measure on the space of sequences you get by, well, if you have an arbitrary sequence of zeros and ones, finite, you can say, what's the chance that you start with that sequence? Well, it's the probability of your starting state times the probability of your transition probabilities for that sequence. So if they're both a half, then it just gives you mass half to the power n for a sequence of length n. So the cylinder set, all sequences that start with this vector y from I is 0 to n minus 1, and that has mass 1 over 2 to the n. Okay. If you have this Markov chain, you can also go back. So instead of saying, well, Pij, that's the transition probability to go from state I to state j, you can also think about the inverse transition probability. So Qji is the chance that previously you were in state I, given that you're now in state j. So with the Bayes theorem, you can express that in Pij, and in the S of I and S of j, those are the stationary weights, stationary masses. So this gives us the transition probabilities for the inverse Markov chain with the same stationary measure. And using these weights, you get equidistribution on your Markov chain, and you converge to the same measure. Okay, so if you have a Markov chain, you also get equidistribution. So let's look at a polynomial that gives, and going towards transcendental functions, or towards working towards some particular transcendental functions. So imagine you now have a degree 3 polynomial, which is really here what's called a polynomial-like map. I'll define it in a bit, but it's a proper holomorphic map from this disk to the whole ellipse, but also a map from this disk to the whole disk. So then a point has 3 preimages, 2 on the left and 1 on the right here. And well, having learned from what we just saw, half and half, I'm going to split the mass, half here and half here. I'm going to give these each 1 coordinate. This is, of course, not optimal. It's not going to give us our measure of maximal entropy, because really we should be taking a third, a third, a third. But it's a possible way of taking a mass. And if we start with a point and we look at preimages like this, we're going to get an invariant measure whose entropy is slightly less than log 3. Then we can make it more complicated even. So this the ellipse that we have, we can map it 3 to 1 and to another circle or topological disk, and then we can have a 3 to 1 map here again, but then add another 1 to 1 map. So now we have a degree 4 polynomial, or polynomial-like map. And then if we take a point here, it has 4 preimages, 3 of which were in this previous, what's that? Well, an annulus, this one minus that one, and 1 here in this. But we can't say that this point corresponds to that point and this one to the, we can't say how they correspond to the previous points, because it depends on the path we've taken from this point to that point. If you go around a critical point, they perturb. So it doesn't make sense to say, well, this point should get weight a quarter and that point should get weight a half. They're at this stage, they all look the same. So no matter how you do it, if you don't give them constant weights, and we can't give them, well, if you don't give them equal weights, and we cannot do for transcendental functions, then we also cannot give them constant weights. The weights must vary as your point W varies over the plane. Okay. So that looks difficult. And now imagine that this at different scales, this happens infinitely often. So this is just a hand-drawn picture. I have my blue, let's say degree 3 map here. I take a blue circle and I take its inverse, and let's say I have a proper map here, degree 3 with a Julia set inside in blue. But then on a much larger scale, this is not a correct picture. You should imagine the green being so large that you could never see it if you're also looking at the blue scale, but it's a much larger scale. You have a degree 4 polynomial with its degree 4 Julia sets here. And then at a much larger scale, again, you have a higher degree polynomial map with an orange Julia set. And the orange really contains the green and the blue, and the green contains the blue, etc. So you can build transcendental functions that have this behavior, that are like polynomials at infinitely many different scales. So maybe these maps will allow us to, well, build a Markov chain. And if we have a Markov chain, we have candidates for what the weights are. Maybe we can get infinite entropy for those maps. So let me go through the definitions. So suppose you have two topological disks, U and V, U contained in V, strictly contained. Then the polynomial map is a proper holomorphic map of some finite degree, at least two. Proper holomorphic map from the inside to the outside. So an example is a polynomial, the simplest kind of polynomial-like map. So if you have a polynomial, so you have a dominating term, the largest degree term, then if you take your radius sufficiently large, then you take a disk with that radius and you take its inverse image, which will be strictly contained in that disk. And then the restriction from the smaller set to the big disk is polynomial-like of the degree of the polynomial. So that's the simplest kind of polynomial map. Now, suppose we have a transcendental function, a function with infinitely many non-zero coefficients. And suppose, moreover, that I chose here, let's say they're all non-zero, but that's not important here. The important part is that I first fix A0, and then having fixed A0, I choose A1 sufficiently small, and then having chosen these, I choose A2 sufficiently small, and so on. Then, well, suppose you have fixed A2, then you can choose your radius corresponding to your degree 2 map. And having chosen this radius, you can take A3 so that you get a perturbation that's really small on this fixed disk. And then you can take a radius for your degree 3 map, and so on and so on. So you get a map that is polynomial-like of every single degree of at least of arbitrary sequence of degrees. So that looks like a family of maps for which you may be able to get something nice. So let's see. Well, if you have a polynomial-like map, then this equidistribution story, it also works that, and you get a measure of maximal entropy log D on its corresponding Julia set. So you have this sequence of measures. So immediately it follows that whatever definition you take of topological entropy on this non-compact set C, it's going to be infinite. And here's a naive idea for constructing mu. I can just sum these measures with weights so that it is again a probability measure. I get an invariant probability measure of infinite entropy. However, this is not an ergodic measure, of course. If I take the Julia set of this mu2, the support of mu2, and I look at everything that lands in there, that's a completely invariant set, yet it has measure half. And that's not allowed. A completely invariant set should have measure 0 or measure 1. So, and you see from the definition, it's not an irreducible measure. You can split it up into many pieces. So this is not what we're going to do. So what are we going to do first? Well, we're going to make the map simpler, because these transcendental functions, they look simple, but in fact, they're not. They can, for example, have any type of periodic orbit, because you can go out and encounter some critical points nearby and come back exactly onto where you started. So in fact, these transcendental functions are more difficult than any polynomial map you can imagine. So Bishop had an idea quite a while ago that you can construct Julia sets of Hausdorff dimension 1 for transcendental functions that are of this type, but you can choose them more precisely so that all critical points go off to infinity. And not just in the long run, but in fact, the orbits are strictly increasing and go to infinity exponentially fast. And I'll sketch how you can do that in a minute, but we'll call these maps Bishop maps. Maybe there are more classes that can be called Bishop maps, but for now, for today, these are the Bishop maps. So how can you construct them? Well, you can take a sequence of annuli. So you take a big annuli, and if you're working with a degree 2 map, then the modulus of the image is going to be, well, much larger. And if you're away from the critical point, then it will contain a round annulus. The image will cover a round annulus of the same modulus, but with lots of space to share. So let me show that picture here first. So here's an example. This is a computer simulation. I took an annulus and I took an explicit polynomial of degree 5 here. And I looked, I mapped it forward. And then I looked at what are the points that are mapped to the next annulus of the same modulus. And that's here with it's drawn with the brighter colors. And you see there's lots of space here. And since the degree 5 map, it's a 5-fold covering. So the black curves are the curves that are mapped to the positive real axis. So I hope that this picture is clear. This is an honest degree 5 polynomial. And here the same picture for degree 6 polynomials. You see that the brightly colored annulus, so that's the pullback of a next annulus. It's not a round annulus, right? It's slightly perturbed. So, but then after a while, you have to switch from degree 5 map to degree 6 map, or from degree 6 to degree 7. And when you do that, you encounter a critical point, or a critical point is created. And you have to make sure that that critical point does not lie in the annulus, but jumps over the annulus. So here, the critical point will be, I took polynomials with positive real coefficients. So the critical point will be on a negative axis, just inside, and jumps way, well, either to this side or to that side. It jumps well over the annulus. And inside the annulus, there is a new disk that is mapped to the origin, to a neighborhood of the origin. Just by counting degrees, you see that the disk you started with has to be covered. Okay, so here I cheated a little bit because actually this pre-image of a disk around the origin is tiny, so small that you cannot see it. So I knew where it was, so I put a big blue dot here. For the rest, the picture is honest. So this is the picture of the Julia set for Bishop maps. You get the big blue circle. This is not a computer picture. I hope you see. This is just hand drawn with a little bit of technology. But this is a fake picture. This is just how I imagine it. You have this blue circle. That's a circle of points that stay in these annuli. So it's the middle of the annulus, roughly, and it goes to inside the next brightly colored annulus, and so on and so on. So all these points go off to infinity. But then they're preimages inside these disks. You get preimages of these circles, and you can pull them back to the beginning. So you get many circles that are very close to that circle, and then you have even more littler circles that accumulate on all of those circles. So Bishop had to do a lot of analysis to first estimate how smooth these circles can be, and then how fast they shrink in order to get house of dimension 1. I'm sure that the people that come to Quasiworld can imagine what kind of estimates you need to get house of dimension 1. So this is the sketch of the global behavior. You have this annulus here. It's mapped 2 to 1. It covers the next annulus with lots of space, and that goes on and it goes on and goes on until you get to degree 3, and you have to choose your degree 3 coefficient carefully so that the coefficient, the critical point doesn't lie in this annulus but jumps over it. But when you have this degree change, you also have some disk that maps back to your original, to your start of your dynamics. And this you have to do infinitely often. So after a while, you get degree 4, degree 5, and so on. So now we have a Markov chain. We have a picture of the dynamics with states that are covering other states 1 to 1. So here in the annulus, I had drawn the curves that I mapped to the real axis that separates an annulus into finitely many cells, 2 cells, 2 cells, 2 cells, but then here 3 cells. And each cell univalently covers all the next ones, but every once in a while, one of the cells also covers the original cells. So this is a directed graph. And now I want to define probability, transition probabilities to get a Markov chain. But this is much more concrete than just an arbitrary transcendental function. So here you have an opportunity to get inspiration. So here's an easy choice. I take a measure or mass half on this initial state, and then all the states together where you have degree 2, I give that mass C2, and all the states together where you have degree 3, I can give it mass C3, and so on and so on. And as we go forward, we distribute the mass as evenly as possible. So when I draw this arrow here, it's actually 4 arrows. From this point, you can go to this one and to that one, and from this, you can also go to the next 2. And I just give them each 1/2. So here I know exactly what I want my transition probabilities to be, because I want high entropy. So I want things to mix up as much as I can. And here I give them all 1/3. But here you have to be a little bit careful, because the transition probabilities for going back, they should be exactly right to get this stationary measure with this mass. So, but it turns out that when you make these axioms, and you give them these masses C2, C3, C4, etc., and you know the number of steps, then that completely determines the transition probabilities. So you have no freedom left. So you have a unique, and it's also ergodic. So for ergodic, you have to check that it's aperiodic, but that's automatic because you have a loop here. You have to check that it's irreducible, that you can go from any point to any other point. You can probably see right away that that's true for this directed graph. So those are properties of the directed graph. And then the final property, when you have an infinite state space, is that from any state, the expected time it takes to go from any state to any other state is finite. That's called positively recurrent. If you have these 3 properties, your Markov chain is ergodic. You have the unique stationary measure, and it induces an ergodic measure on the space of sequences in the Markov chain. And then you can compute the entropy, and it turns out that when you choose Cn, like 1/n log n squared, then you get infinite entropy. Now, if that sequence may seem fancy, but it has to be something. It has to be something that converges, right? Because I want the total mass to be 1. So 1/n log n squared converges. And if you do the estimates, you get that log n times this. The sum of that should be infinite. So, well, 1/n log n is not summable. So this is an easy choice to make. But really, you have a lot of freedom here. In the Markov chain that we had with this half-half, you had no freedom. If you took different numbers, it summed up to something that was strictly less. But here we have an infinite sum, and if you choose you vary one of the numbers a little bit, you still get infinity, right? So there's a lot of freedom, and every different choice of your transition probabilities gives you a different measure. So in fact, you have infinitely many measures here. Well, infinite dimensional space of measures that all give you infinite entropy. So this idea that we should get a unique measure of maximal entropy, that's just false here. That will never be true. And then I should point out that actually when we went back from this state to this state, we could also go back to any other state. So the measure on the state of sequences I constructed, the support is not the whole Julia set. Because in the complex plane, you can have more transitions than just for the Markov chain? Well, no panic. We can just adjust the transition probabilities very slightly so that they all become positive. And you can argue, well, if you do it small enough changes, the system remains positively recurrent and the entropy remains infinite. So you just make all the possible transitions corresponding to your complex dynamical system, make them slightly positive, and your properties are preserved. So I already discussed the solution. So here is the theorem. For any Bishop map, you have a Markov chain on a countable set. You get an induced ergodic measure of infinite entropy here. And you have a continuous map from your space of sequences to the Julia set, which is homeomorphic outside of the subset of measure 0. So for the Cantor set, you get a homeomorphism with the Julia set, the degree 2 map. But if you just take z squared, then you have the action on the circle. Well, the circle is not homeomorphic to a Cantor set. There are some identifications there. So you can't expect a homeomorphism here because we have these circles. But it's good enough because the set of measure 0 doesn't matter for pushing forward the measure. So we get a measure on the complex plane. So the symbolic dynamics outside of a set of measure 0 gives us an ergodic measure in the complex plane whose support can be the whole Julia set, but it could also be a proper subset. The first we constructed was proper. The second one, by these adjustments, the support was all of the Julia set. And then you can observe that anytime you have such a Markov process, you also get equidistribution of preimages, and you also get equidistribution of periodic cycles. That's almost for free. So these are very pleasant maps, and to my mind, understanding this measure can give you even better understanding of the dynamics of these transcendental functions. But it's also a very restrictive class of maps. So let's see. Well, if you take any finite order transcendental function of disjoint type, and I won't go through the definitions, but here are two examples. This is the sine of z over 2 that I discussed earlier. This function on the left is e to the power z plus z minus 2. So on the left half plane here, the exponential of z is smaller than 1. So there you have a translation to the left by at least 1. So the whole left half plane is going to infinity in the left-hand direction. And on the right, your exponential is periodic with 2 pi I. So you have, this is just one period that I'm showing. You have also these infinitely many curves with endpoints. In fact, theory, maybe this goes back to Baker for these maps, but many people have worked on this. Lasserempe is a name that comes to mind. Many people have worked on describing this. This is really a Cantor set of curves, and the action on these, you can describe it symbolically, and you get a very large subset of, well, this enormous space of sequences n to the power n, but that contains our previously constructed Markov chain. So the Markov chain we constructed for these much simpler functions embeds into n to the power n. So we get measures there. They're very far from the whole Julia set, but then we can do the same trick again by for every transition probability, we can make it slightly positive, and we get the whole Julia set. So also for these systems, you get measures supported on the whole Julia set, whose support is the whole Julia set, ergodic measures of infinite entropy. Now, let me see, I don't want to take Nuria's time. I still have a little bit of time. There's one third class of maps that I'd like to discuss, which is, well, the class of maps that I discussed previously. What if you don't take these very nice bishop maps, but you just take any sequence of coefficients that decreases sufficiently fast? Well, if you really let them go to zero very fast, then you still get that you get equidistribution. You don't get a Markov chain, at least I don't know how you get a Markov chain, but you get equidistribution. So what's the idea of the proof here? Well, what you do is you make a bishop map with the same number of steps. That gives you inspiration for what weights you should take for the equidistribution. And then you use these weights for the above map. And then you argue, well, you get convergence. And well, if the number of steps is large enough, you get small perturbations of this infinite sum, it will still be infinite. That's the idea. So let me discuss some steps in the proof of Lubitsch for showing that you have equidistribution for rational functions. What you do is you define a transfer operator. So AF of a continuous function is just, well, what is it, pull back or push forward the function. The value at Z, the value at W is now, you look at all inverse images and you evaluate phi, the continuous function, over those inverse images, and you average. Well, and now you want to prove that for any continuous function on the sphere, applying this transfer operator repeatedly gives you an equicontinuous family of functions. So an important step here is that if you take any point, you take a small disk, then if you pull back, then the diameter of the inverse branches shrinks to zero. Well, you look at the inverse branches that don't hit the critical points. That gives you a normal family, and then you shrink to zero. Then it follows from this that your sequence is equicontinuous. And you have to argue that the unitary eigenvalues are the constant functions. And then there's a result that it follows that pulling back or applying the transfer operator repeatedly, that just converges to the measure of some, well, the integral over some measure, mu, and that's your measure of maximal entropy. Now, this proof, you have to adjust it a little bit for it to work for the transcendental function. So you have infinitely many preimages. Well, we now know what to do with that. But the weights, they vary with the base point. So that's an issue, because when you have these inverse branches and they land in regions where these weights vary, then as you pull back, the argument to get equicontinuity doesn't work anymore, because different points in that little disk will have different weights for the preimages. So what you should do is you make sure that the weights vary smoothly, and then you argue that most inverse branches shrink exponentially fast. And why is that true? That's also true for rational functions. So you look at the univalent branches, the univalent inverse branches, then by shrinking the radius, you obtain bounded distortion because you have a normal family. Now the total area is finite, so you look at, well, how many bad disks there could be that are still large. Not too many, you throw them away, and the remainder must shrink exponentially fast. And then when you have bounded distortion, if you have area estimates, you get diameter estimates. And the same holds in the transcendental case, but now you don't count how many inverse branches are good, because they're infinitely many, but you look at what's the weight of the good inverse branches that shrink exponentially fast. And so it's still true that most inverse branches shrinks exponentially fast. The weight can be arbitrarily close to 1. And so you smoothen the weights, and then you get equicontinuity of the pullbacks. That's the argument. Okay, so that's here's my last slide. So future work, I would like to do it for arbitrary transcendental functions. I would very much like that, but I have no idea how to do it. So we think we know how to do it for transcendental Halo maps, but with one caveat, it's not clear yet that we get the full Julia set. The support of the measure could be smaller than the Julia set. And that's actually, for polynomial Halo maps, a famous problem is the support of the Julia set equal to the full Julia set. So also for our examples, I don't know yet how to argue this. And then I would like to understand this connection to conformal measures better. And that's it. Thank you very much.
Yeah, let's thank the speaker.
It's always awkward to have these muted people clapping for you because you think they're clapping, but you're not sure.
So are there any comments or questions?
Maybe I have a question. Just curious, I mean, I always understood that this heavy machinery that people use in several variables, right, bifurcation measures, etc., all start with the existence of an invariant measure of maximal entropy, right? I don't know. I'm just wondering whether you have in mind some kind of a first step for developing a similar machinery, or you think that this is hopeless in the case of entire maps, or?
Well, all entire maps is hopeless. There are
Yeah.
too many of them. But so the machinery we use to get the invariant measure for transcendental Halo maps is, I think, in spirit quite similar. I'm not sure what you're referring to with the heavy machinery. It's a little, what I consider heavy machinery is very different from what you would consider heavy machinery. But
Probably.
You get these forward, for the Halo maps, you have to look both in forward time, in which case your points lie on stable manifolds, and then in backward time, and they lie on unstable manifolds, and you have to argue it's the intersection of the stable and the unstable manifolds. That's where the measure lives. And I think that's in spirit quite similar to what people do for the polynomial for the polynomial Halo maps. I'm not sure if that's an answer to your question.
More or less, more or less.
So are there other comments or questions? So let me actually ask a question. Is there any hope maybe to get some description of all the ergodic measures of infinite entropy, or is this completely hopeless?
Maybe for the Bishop maps you can understand it so well.
Yeah, I mean, of course,
it looks very difficult. Looks very difficult, even for that Markov. We basically have to look at the Markov chain.
Yeah,
right?
because
you have the Markov chain of.
You have this special construction of your measures, right? But
right.
somehow are the measures that you obtain in this sense, are they somewhat typical, or what's your?
Yeah, that's a good question. It looks like a difficult question, but I haven't considered it before, so I will think about it again some other time. Thank you.
Other comments or questions?
Yeah, I have one or two questions maybe. So I think if I understood correctly, you only make your transfer operator act on continuous functions, right? You don't care about regular. So can you make them act on some other norm, like Holder norm, or like subharmonic functions, something like that?
Yeah, maybe. I'm not sure you would.
If there's a related question, maybe you can
way.
answer some other way. Can you tell something about like the regularity of your invariant measures, like Holder regularity or something like that?
Not yet. No, good question, but I haven't thought about it. It's too fresh.
Okay, yeah. No
it's
problem.
a good question.
Okay.
Are there more comments or questions? Lucas, you said you had two questions.
Yeah, I asked them both. together, so they're related.
So for the entire maps, so we should look at either continuous mapping functions on the sphere, or maybe bounded continuous functions. I think both will do, but not continuous functions on C doesn't work. You have to deal with the behavior in your infinity.